Hello, in this video I'm going to be solving exercise 1.4.103 from Jiří Lebel's Notes on Diffy Qs. So suppose a water tank is being pumped out at 3 liters per minute. The water tank starts at 10 liters of clean water. Water with toxic substance is flowing into the tank at 2 liters per minute with concentration 20 T grams per liter at time t. So this isn't a typo. This is supposed to be 20 times t right here. When the tank is half empty, how many grams of toxic substance are in the tank, assuming perfect mixing? Okay, so let's first set up our differential equation for the amount of salt or the amount of toxic substance in the tank at time t. So first, I'm going to let x at t be the amount of toxic substance. At time t. So my first goal is going to be to find an expression for x at t. So then I can move on to this, what the thing is actually asking. How many grams of toxic substance are in the tank when the tank is half empty? So, as is usual with these mixing problems, our differential equation that we're going to solve is going to be set up like this. So our derivative dx dt is going to be the rate in times the concentration in minus the rate out times the concentration out. And let me move this for space. There we go. And so what we need to do is determine what's the rate in, concentration in, rate out, and concentration out. Now, the first three are easy. We're given that the rates in up here is 2 liters per minute. That's the amount of water with toxic substance flowing into the tank. So this is 2 liters per minute. The concentration in is also given. Let me just write this. This was given to be 20 T grams per liter. So this is 20 T grams per liter at time t. Rate out was also given. The water is being pumped out of the tank at 3 liters per minute. So rate out equals 3 liters per minute. But the concentration out is something we need to determine, right? Okay, so first I'm going to make a schematic of what's going on. Here we go. And I'm going to add a little faucet right here for all the water flowing out. And then I'm going to draw the water flowing in too. So, and then here is our water. And then this is the water pouring in. Okay. And again, the water is flowing out this way. So what we want is the concentration here in this faucet that drains out the water. But, and you know what, just for fun, I'm going to draw all the toxic waste coming in to our clean water and polluting it. Poor thing. I can't draw a skull. I'm not going to try. Okay. So we want to determine what's the concentration of toxic substance in our little faucet at time t. But we're given that the tank is being perfectly mixed. So if the tank is being perfectly mixed, we can fix our image here so that all the toxic waste is evenly distributed throughout the water. What this means is that the concentration of toxic waste, toxic substance inside of our pump our little faucet pumping out, that concentration has to be the same as the concentration in the rest of the tank. But what is that concentration? Well, at time t, actually, concentration now equals the concentration in the tank by what I just mentioned. And once again, because we're stirring everything perfectly, the concentration of toxic substance inside the water of the tank is the same as the concentration of toxic substance flowing out of the tank. But what is the concentration in the tank? Well, this will be the amount of toxic substance in the tank at time t divided by the volume at time t, or the volume of water at time t. Now let's denote the volume of water by capital V of t. So I'm going to let this be V of t. We know what this is at the top. This is just x of t. Again, we let that be the amount of toxic substance at time t. So the top is just x of t. And now we've declared the bottom to be V of t, and we need to figure out what V of t is. Okay. So initially, we were given that the volume of water inside the tank was 10 liters, okay? So initially we had 10 liters of water. But because we're flowing in water and pumping it out at the same time, we have to correct for the difference in water that has been overall net added or net subtracted after what's our unit of time, t minutes. And what this means is that this is going to be the initial volume of water. So initial volume of water. And we're going to do plus the amount of water coming in, rate in of water, times t, minus, and we're going to, so we're taking the amount of water we're adding in, and then we're subtracting the amount we're adding out, and that's going to give us the net change in the amount of water. Rate out of water, also times t. And okay, we can simplify this a bit. So V0, we know that to be 10. And then if we factor out these t's right here, we get this rate in of water minus rate out of water times t. And let's just take a minute to check that this formula makes sense. Okay. So if the rate in of water, if the amount of water going into the tank is greater than the amount of water being pumped out, then this difference will be positive. And therefore, this entire expression is going to increase because we have this constant, and then this is a linear function with a positive slope at that point. If, on the other hand, the rate in of water is less than the rate out, as in our case, because we're given that water is flowing into the tank at 2 liters, but it's being pumped out at 3 liters per minute, then this difference is going to be negative. And so now we're going to have a linear function with a negative slope, and so that function is going to be decreasing. Okay, that checks out. And now just plugging in our numbers. So this is 10 plus, and we were given that the amount of water going in is 2 liters per minute. And then the amount of water being pumped out is 3. So this is times t. And so our final expression for the volume is 10 minus t. At this point, I should make comments that's going to be important for us in just a bit. So notice how this implies that the volume is, notice, V of t becomes 0 at t equals 0. So after 10 minutes, there's going to be no water left in the tank, which makes sense because we're pumping out more water than is flowing in, right? But importantly, because we care about when the tank is half empty, we're considering times before. So when the tank is half empty, that occurs before it is fully empty. And so what this means is that we will assume that t is less than, oh, that's a typo. And let me be more complete. So what this means is because we care about the time at which the tank becomes half empty, and we know that time occurs before the time at which the tank becomes fully empty, we will assume, since we care about when the tank is half empty, we will assume that t is less than 10. Again, because we know that the time at which the tank becomes half empty has to be less than the time at which it becomes fully empty, because the amount of water in the tank is decreasing, as we see right here. Okay, and this is going to be important for, in just a bit, you'll see. But anyway, turning to the next page, what this means is just plugging in all the numbers I had from the previous page. Our rate in, once again, was 2 liters per minute. Concentration in was 20T. And we're subtracting the rate out, which is 3 liters per minute, times our expression for the concentration out, which is x of t over v of t. But we know what v of t is. This is 40t minus 3 all over, well, v of t, I'm going to move over the x of t to the right. And we know v of t is 10 minus t. So this is 10 minus t. And so rearranging, we get this linear differential equation, dx dt plus 3 over 10 minus t x of t equals 40t. Nice. Okay, so we have a linear differential equation. So to solve these, as always, we have to get our integrating factor first. And we need to look at the coefficient function in front of the x of t. And we're going to take its exponential, e to the integral. We're going to take the exponential of the integral of that coefficient. So e to the integral of that coefficient function. Now, this is e to the, just doing some mental substitution, this is e to the negative ln absolute 10 minus t. And we can simplify this a bit with properties of exponentials to be 3 ln 10 minus t. And then 1 over 10 minus t cubed, because the e and the ln cancel each other out. But now this is where that comments I made, where we're assuming that t is less than 10, is going to be important. So since we are assuming that t is less than 10, this simplifies to, because the absolute value brackets are going to, oh, wait. I should add first, i.e. 10 minus t is bigger than 0. Just by rearranging this inequality, we get this. This tells us that the stuff inside the absolute value brackets is positive, and so we can just drop those absolute value brackets. And this gives us our final integrating factor as 1 over normal parentheses 10 minus t cubed. And so going back up to our differential equation here, if we multiply by that integrating factor, we're going to get 10 minus t cubed dx dt. Oops. Plus 3 over 10 minus t to the fourth now times x of t equals, what's it going to be? 40t all over 10 minus t cubed. And so the left side, we can recognize this as a product rule. This is just the derivative of 1 over 10 minus t cubed x of t. So it's just our integrating, it's always going to be the derivative of our integrating factor times our function x of t. And so if we take the integral of both sides, we're going to get that this is, oops, let me move this over. And integrating gives this, which I'm about to write. Integral 40, and then we integrate the right side. So this is 40t over 10 minus t cubed dt. And I'll skip through the, no, actually I won't. So I'll walk us through this calculation. So now we're left with evaluating this integral. I think the easiest way is to just let u equal 10 minus t, which gives negative 40. And if you change all your variables, 10 minus u all over u cubed du. And this in turn is negative 40 times the integral of 10 u cubed minus 1 over u squared du. And this will be a negative 5 over u squared plus 1 over u plus our constant c. And just turning a page, what we got is that this x of t is equal to, and now we just distribute the negative 40 over. So this will be 200 over, plugging in our u back, we get 10 minus t squared, and then minus 40 over 10 minus t. Wait, did I get that right? Yes, 10 minus t. Plus our constant c. And so, here at this point, we could multiply both sides by 10 minus t cubed to get our final expression for x of t. But I think it's actually wise to use this moment here as written, use our expression as written to figure out what the constant c is. I think it makes it a bit easier. Now, how do we find this constant c? Well, we need some kind of initial condition, right? And if we turn back to the problem statements, recall that the problem told us that the water starts at 10 liters of, and this is important, clean water. Now, clean water does not have any of the toxic substance, and so what this means is that at time t equals 0, our amount of toxic substance is going to be 0. So this is 0 when t is equal to 0. So to find c, use x of 0 equals 0, again because the water was clean at time t equals 0. And we get that, well, the left side is going to be 0. So we get 0 is equal to 200 over 10 squared minus 40 over 10 plus c. And so c is going to equal, well, it's going to be 4 minus, this number is going to be 2. So this is 2. And therefore, plugging this in to our expression up here, we get 1 over 10 minus t. And you know what? I'm going to kill two birds with one stone. I'm going to multiply the 10 minus t cubed over to both sides. And so Simplifying everything involved, this gives a final expression for x of t as the following. 10 minus t minus 40, 10 minus t squared, plus 2 10 minus t cubed. Nice. What's next? So now we get into the actual thing that this problem was asking for, which is when the tank is half empty, how many grams of toxic substance are in the tank? Now, I should point out here that this is where the problem gets a bit ambiguous because they never specifically stated what the volume of the whole tank is. They did tell us that the water tank starts at 10 liters of clean water. And so you might draw this like this. So here's our tank. And you know what? I'll make it smaller just to make this point I'm going to make. And maybe the water is here and this is 10 liters. But what's stopping the scenario that's given to us from looking more like this, where we have the same tank right here, but, and I made a mistake here, it goes up way higher to look more like this. And yet we still have the same amount of water at the beginning, so it's still roughly about this high, and this is still 10 liters. So the problem is a bit ambiguous in that sense. The good thing is, if you just sit and think about it for a moment, because the amount of water is decreasing in both scenarios, again, we're not changing the amount of water we're pumping out, we're not changing the amount of water flowing in. The amount of water inside the tank at time t is going to be the same in both of these scenarios, no matter what the volume of the whole tank is. And in particular, our function x of t, the amount of toxic substance inside the water is still going to be the same by the same logic. And so for our purposes, we can just assume that the tank actually has a starting volume of exactly 10 liters. So again, there's nothing differentiating any of these scenarios here. And so we might as well just assume that the volume of the tank is 10 liters. Because the math plays out exactly the same in all three ways. So going back here, assuming the tank is 10 liters, 10 liters. And you know what? I'll rephrase. Can contain 10 liters. Can contain 10 liters of water. We want to know how much of the toxic substance there is at the time when the tank is exactly half. Okay, we want x of t0, where t0 is the time where the volume of the tank is halved. It's half. This is where we're going to use the expression for the volume that we had earlier. So now, because the volume of the tank, since the volume of the tank is the same as the volume of water in the tank, as the initial it follows that And let me rephrase. The volume will be half when the volume of water inside the tank is equal to 1/2 of the total volume of the tank, which is 10, and this is equal to 5. Where, again, V of t is the amount of water inside the tank. But we know what this volume is. We know that V of t is 10 minus t. So, and here I should use t0 for the time when the tank is halved. So t0, if we just solve this equation, 5 equals 10 minus t0, this gives us that t0 is equal to 5. And now that we have this, we can go back to our expression for x of t, and what we find is that the volume of interest is 200 times, well, 10 minus 0 is 5, so this is 5. Minus 40, still 5, but we square it. Plus 2, and then we cube 5 here. And this will be 1,000 minus, wait. 25 times 4 is 100, 1,000. So this is 1,000, this is 1,000, and then the final number here is 2 times 5 cubed, which is 2 times 125, which is 250. And so our final answer, which agrees with the book, is that the amount of toxic substance is 250 grams. Okay, that wraps up this video. If there are any questions, please feel free to leave a comment. Otherwise, I will see you all in the next video.